when we look at the graphs of what slices of a cone would give you, we get things called a conic section. There are 4 different shapes that we can get depending on the way that we slice a cone. One is a parabola, another one is a circle, another one is an ellipse, and then the 4th one is a hyperbola. In this video, we're going to talk about a parabola, what its definition is, and then what are some key components that we can look at in order to either write the equation of the parabola, or from the equation of the parabola, how we get some important pieces about the parabola so that we can go ahead and graph it. First, the definition. A parabola is the set of all points in the plane equidistant. Remember, equidistance means that the distance is the same from a line L, called the directrix, and a fixed point F, called the focus. Now, it's very likely that you've seen parabolas as functions prior to working with the other components of a parabola when you think about it as a conic section. When we looked at parabolas just as parabolic functions, mainly the thing that we were interested in was, what's the vertex? Is the parabola going up or down? And then, does it have a vertical or horizontal stretch? Has it been shifted horizontally or vertically off of the origin, which then again gives us that information about the vertex? In the concept of looking at it in terms of its real basic definition, we get these other key components of a parabola that actually gives us more structure about the graph and also some applications that we can use with parabolas. So the other key components to it that we usually don't talk about in earlier work with a parabola is the focus and the directrix. But they are really important components of a parabola. In fact, when you look at even our dishes that we have to collect signals from satellites, those are parabolas that have been spun around to make a parabolic dish, and that arm that's sitting out there with the receiver, that receiver is at the focus of the parabola, so that the lines coming into the parabola bounce off and then accumulate at that receiver and send the stronger signal into your homes. If we put a bulb at the focus of a parabolic reflector, then that shoots out the beams of a flashlight in more parallel beams instead of just scattering it out. So there's a lot of applications in real life settings that the shape of the parabola and these extra key informations about the focus and the directrix are helpful. So just kind of getting a picture of this with these other key components, when I think about how this goes with the directrix and the focus, if I have a directrix that's vertical and I have a focus that's to the right of it, then the parabola is all those points that are equidistant between the focus and the directrix. So like here, and then if I do equal distances, you get that the parabola always curves around the focus and away from the directrix. So if my directrix is vertical, then my parabola is either going to open to the right or my parabola is going to open to the left, depending on what side of the directrix your focus is on. If my directrix is horizontal and my focus is above the directrix, then equidistant between here, I'd have that point where my vertex is, and it would curve that way. If my directrix was horizontal and my focus was below it, getting your equidistant, and you get your parabola going down that way. So it's important to notice that the parabola always curves around the focus, and the parabola is equidistant between the directrix and the focus. So the vertex is actually sitting between the focus and the directrix, equidistant there. Now this distance between your vertex and your focus, that's this small case value p that we'll get in the way we rewrite our parabola equation. And when I look at how this is rearranged to get this specific information off, what's the p, how we can get our equation of our directrix, it's a rearrangement of the way that we do our equation for a parabola that helps us get that information. Now, if you recall when you were working with parabolas, when there are functions, you always got the y on a side by itself is equal to ax squared plus bx plus c, or you wrote it in vertex form, y equals a times the quantity x minus h squared, and then plus your k. So we got the variable that was to the first power on one side set equal to the variable that has the square in it on the other side. When I want to figure out the focus, the directrix, as well as the vertex, we arrange it differently. We arrange it so the variable that has the square on it gets to be on a side by itself, and then with its shift, and then the first degree is on the other side, and the coefficient that's out in front of that then is 4 times your p-value, and that 4 is consistent throughout the definition of it. So if it's y minus k squared is equal to 4p times x minus h, those are the parabolas, well, if the y is squared, those are the parabolas that go right or left. And it's opening to the right if your coefficient 4p is a positive number, and it'll open to the left if your 4p is a negative number. And then this x minus h squared is equal to 4p times y minus k. Those are the ones that are going up or down. And up if the 4p is positive, down if the 4p is negative. Now notice that h is always with the x, no matter which case you have, and the k is always with the y. And your vertex is the h comma k that you're comfortable with from when we looked at parabolas before. Now, if your parabola is a vertex at the origin, then your h and your k are 0. So you would get then the specific forms of it at the origin just by having h and k both 0. So let's look at this idea along with those formulas and do these examples. So first, find the equation of the parabola having a vertex of 1, 3 and a focus of 5, 3. So basically what I need to do is, from that vertex and that focus, which case of it do I have? And once I figure out which case of it I have, then I pick the correct standard form and put the information in. So I always want to graph these when I have information just to be able to get a visualization of it. So 1, 3 is right 1 up 3. And that's my vertex. 5, 3 is my focus. So right 1, 2, 3, 4, 5 and up 3. That's my focus. Now my vertex and my focus are in a horizontal line with each other, and my parabola has to curve around my focus. So my parabola has to go like this. And this point is 1, 3 for the vertex. My focus is 5, 3. So the distance from my vertex to my focus is a distance of 4. And that distance from your vertex to your focus is your p. So p is equal to 4. It's opening to the right. So that's when I have my y being the variable that is squared. So when I look over here, the y being squared is that one. So I have my form y minus k squared is equal to 4p times x minus h. And I notice from the setup that my vertex is 1, 3. Well, the vertex is hk. So h is 1 and k is 3. So my equation of my parabola for this example is y minus 3 quantity squared is equal to 4 times p is 4. And again, we got that from the distance from your vertex to your focus. So 4 times 4 times the quantity x minus My h is my x-coordinate of my vertex 1. So I get y minus 3 quantity squared is equal to 16 times x minus 1. So that's all I wanted you to do there, was to write the equation of the parabola. Now let's look at the next one. Here they give me the equation and I want to find the directrix, focus, and vertex. Now I need to write it in one of these forms, and my y is the variable that's squared, x is to the first power, and when one of the variables is squared and the other one's to the first power, that's when you know you have a parabola. If you've got both variables, highest powers 2, then it's one of the other conic sections if it's not a degenerate case. So here I want to get it in one of these forms. Y is squared, so it's this top one that I'm going for. So we are going to, well, I want to get the y that's squared on the left side of the equation, so I'm just going to switch sides here. So 1 over 16y squared minus 3 over 8y minus 1 is equal to x. Now I want to remove the fractions because notice I don't have a coefficient in front of the y, quantity y minus k squared. So actually I want to get this coefficient in front of the y squared to be a 1. I'll do that by multiplying both sides by 16. So I get y squared minus 16 times negative 3/8 is minus 6y. 16 times negative 1 is minus 16 is equal to 16x. I want to complete the square on the y's. So I want to add the 16 to the other side. So I have it set up to complete the square. And to complete the square, to figure out what number sits here, and you left a space to complete the square, figure 1/2 of negative 6 is negative 3. Negative 3 squared is positive 9. So adding a 9 here will make that trinomial a perfect square trinomial that then I can factor as a binomial quantity squared. But if I add 9 to this side, I also have to add 9 to this side. So I get y minus 3 quantity squared, when you factor this, is equal to 16x plus 25. Now, I also need to have my coefficient of my x in the parentheses to just be a 1. So whatever coefficient is in front of your x, you want to factor it out whether it makes fractions or not. So I have y minus 3 quantity squared is equal to 16 times a quantity x plus, and if I divide out a 16, that'll give me 25/16 as that second term in the binomial that I factored out the 16. So now I have my coefficient in front of the first power variable is what your 4p is equal to. So 4p is 16. Divide both sides by 4, I get p is equal to 4. My vertex, the x-coordinate of my vertex is negative 25/16, and the y-coordinate of my vertex is 3. And then I have to think about which way this is going. My coefficient, once I got my quantity of my y minus 3 squared on a side by itself, my coefficient is positive, and it's the y letter that's squared. So that means this parabola is going to the right. So thinking about it, my parabola is going to the right. My vertex then has to be, my directrix then has to be vertical. My vertex is at negative 25/16, 3. And the focus is in towards the curvature of the parabola. So I need to go right p steps from my vertex. P in this problem was 4. 64/16 added to a negative 25/16 is 39/16. So my vertex, or my focus, is going to be 39/16, comma 3. And my directrix is vertical. The equation of a vertical line is x equal. And it is p units the opposite direction of the vertex than the focus went. So I need to go 4 steps left. So I'm going to have -64/16 combined with the -25/16. So that gives me a -89/16. So my equation of my directrix is x is equal to a -89/16. So when it asks me for the directrix is x equal -89/16. My focus is 39/16, comma 3. Remember, the focus is an ordered pair. The directrix is the equation of a line. And then my vertex is at -25/16, comma 3. So that's the vertex, this is the focus, and the top one is the directrix. So hopefully this video's been helpful in giving you some background information of looking at the extra characteristics that we get for a parabola when we think about it as a conic section, and some of the key components that maybe you had not seen before if you just looked at parabolas and their applications in functions.